Welcome to this explainer. You know, we constantly see robots performing these absolutely incredible feats all around us, right? But today, we're going to pry open that black box of robotics. We are looking under the hood to see exactly how these automated systems actually tick. Because think about it. How does a literal pile of metal know how to navigate the world? I mean, it's a fascinating question to kick things off. We see them seamlessly assembling cars on a factory floor, or, just vacuuming our living rooms without tumbling down the stairs. But how does inanimate matter pull that off? Well, today, we're uncovering the hidden mechanics making the whole shebang happen. Let's dive right in with our core concept, the control system. Basically, this is the invisible force regulating every single action a robot takes to hit its intended goal. It is constantly monitoring, processing, and adjusting on the fly. To unpack all this, we're going to follow a quick four-part roadmap. We'll look at the processing flow, the system's anatomy, so senses, brain, and muscles, then the feedback loop, and finally, the ultimate showdown, manual versus automatic control. All right, let's kick things off with Section 1, the processing flow, from sensing to acting. It really helps to think of this linear progression kind of like touching a hot stove. First up, sensing. That's gathering the environmental data, feeling the heat, right? Then comes data processing, where the CPU, the central processing unit, takes in that raw data. Third is making decisions. The CPU runs its algorithms to evaluate the conditions and figure out what to do next, like realizing you need to pull your hand back. And finally, actuation. That's when the mechanical parts actually get the signal from the CPU to move. Moving right along to Section 2, the anatomy. We're talking senses, brain, and muscles. So, first up, the sensors. You can literally just think of these as the eyes and ears of our system. They are constantly scooping up crucial information about the robot's surroundings and its own physical orientation. Whether it's a camera looking for an object, an ultrasonic sensor pinging to gauge distance, or a gyroscope keeping things balanced, these components are just relentlessly feeding data into the machine. Which brings us to the brain. The crucial takeaway here is that the controller acts as the central nervous system. It takes all that sensory data we just talked about and computes exactly what needs to be done. It's running some pretty complex algorithms. You've got stuff like fuzzy logic, which is awesome because it helps the bot deal with uncertainty and gray areas, or state space calculations for exact physical orientation. All of this generates those ultra-precise control commands. And once that brain decides to act, it relies on the actuators to carry out the command. These are the muscles of the operation guys. By firing up motors, pneumatic cylinders, hydraulic systems, or servos, the controller dictates the exact speed, direction, and position of the movement. I mean, they quite literally breathe life into the robot's behavior. Now, zoom out for a second and look at how this builds beyond just one single machine. Just like we talk to each other, these systems communicate too. This allows for some crazy complex coordination across entire factory floors or even huge swarms of bots. A central unit can use these networks to keep multiple robots perfectly in sync. It's like a highly choreographed dance. Okay, on to Section 3, the feedback loop, or how robots kind of feel. Think about this as a real-time, continuous loop. The input goes to the controller drives the process, and boom, you get an output. But here is the absolute magic step. The robot measures the result of its own action and feeds that data right back into the input so it can correct its own mistakes on the fly. We call this closed-loop control, and this is a massive deal, right? Because it proves these robots aren't just blindly following a rigid script. They're constantly adapting to unpredictability to stay stable and safe. By checking that sensory feedback over and over, they compensate for errors and respond dynamically to sudden changes in the environment. Actually, this is exactly why your smart thermostat doesn't just blast heat endlessly until your house melts. It stops exactly when the room hits that perfect temperature. All right, final section, number 4, the showdown, manual versus automatic control. We are living through a fundamental shift right now, replacing the human operator who literally pulls levers with an automated, algorithm-driven controller. Notice how the automated system completely bypasses the need for a human supervisor just by feeding its measured behavior right back to itself. When we compare the two side by side structurally, you can see control completely shifting away from human experience and over to sensor-driven programming. In automatic control, decisions are handled purely by algorithms and feedback, so it adapts entirely on its own. Manual control, though, that relies purely on a human's real-time observations, meaning if something unexpected happens, a person absolutely has to jump in. Let's break down some of the most striking differences here, starting with the simple fact that algorithms literally never get tired. They don't get distracted. Automatic control gives you consistently high precision because it just follows rigid instructions. Manual precision, well, that is completely at the mercy of human fatigue, our skill level, and our wandering attention spans. And when we're talking about safety and response times, it's really no contest. An automated system can spot a hazard and adjust in milliseconds. Manual systems are heavily bottlenecked by our own biology. If a human operator spaces out for even a fraction of a second, safety is immediately compromised. Because, let's face it, our reaction times are just so much slower. Now, sure, setting up an automated system is going to hit you with a higher upfront cost for all those sensors and controllers we talked about earlier, but it pays off incredibly fast. It can effortlessly juggle a level of complexity that would totally overwhelm a human brain. Manual control might be cheaper on day one, but it struggles hard with intricate, multivariable tasks, and your operational costs stay high because, well, you always have to pay for labor. To really ground this in reality, just think about the difference between physically turning your car's steering wheel versus trusting an aircraft's autopilot at 30,000 feet. Or even just getting up off the couch to adjust a thermostat dial by hand versus a smart system that handles the room temp automatically based on feedback. We interact with these automatic marvels every single day. So here's a somewhat provocative question to leave you with. As these automated systems become infinitely more precise and adaptable than we are, what roles will actually be left for the manual operators of tomorrow? With sensors, controllers, and actuators perfectly mimicking our senses, our brains, and our muscles, but with tireless precision, the gap between human capability and robotic automation is closing faster than ever.